Hello, my name is Don Cadet. This video, we will go over the synthesis of dimethylmaleate, as well as dimethyl fumarate. First off, the purpose of this experiment, part 1, is to synthesize dimethylmaleate, also known as dimethyl 2-Z-bute-2-enedioate. Dimethylmaleate is utilized in many industries because of its chemical properties. For example, it is used as intermediates as well as an additive for agricultural products. It is used in the pharmaceutical industry. And overall, just by looking at the structure of dimethylmaleate, which is right here, we're able to see its redrawing effects. Because of this, it is commonly used as a dienophile for Diels-Alder type of cycloaddition reactions. And once dimethylmaleate forms, we're able to see a colorless clear liquid, oily substance, with a melting point of -17 centigrade and a boiling point of 204 centigrade. Furthermore, it has a density of 1.15 grams per milliliter. So right here, we're able to see the anhydride. And the first step is the methanol being deprotonated by the sulfuric acid. So because of this, we're seeing the anhydride reaching in and grabbing one of the hydrogens, or the one on the oxygen, the one that is having a positive charge. So right now it is protonated and it leaves the carbon right here being more vulnerable than it was already previously. So we have the deprotonated methanol being able to nucleophilically attack. We have we're the monoester right here. We're forming that monoester. So we're able to do this again, but this time we're having the OH grabbing in on the methanol and deprotonating the methanol right here, and we're leaving with oxygen, which having two bonds, or actually three in total, 2 hydrogen bonds and 1 carbon bond, leaving that to be positively charged. So that deprotonated methanol is able to attack again at the carbonyl carbon, and we're able to see the attachment, and we are getting to dimethylmaleate as in have our byproduct of water and H2SO4. Our byproduct H2O is because of this being kicked off right here. So, and then we also have H2SO4 as our acid catalyzed. So moving on, there's many things that we need to talk about on the experimental setup. Dimethylmaleate is synthesized from reagents maleic anhydride, methyl alcohol, sulfuric acid, which speeds up the reaction. We have water as a byproduct of the reaction, and 5% sodium bicarbonate. It is used as a drying agent for excess water. So we are able to see the CAS number, which is the identification number of all these reagents, as well as the molecular mass melting points of all of these. So we have methyl alcohol, sulfuric acid, water, of course. So let's move on. The materials needed. So I will talk about the procedure more precisely, but it is wise for me to talk about the materials first. Those materials include the Hickman steel thermometer, calcium chloride, reflex condenser, which we will talk about later, a little bit more later, spin vane, conical vial, a steam apparatus, and pipettes. Let's move on. So the starting material, maleic anhydride, was analyzed and characterized using IR and HNMR spectroscopy. So we found that there were 4 major signals in the IR spec. So 2 alkene functional groups, one being a double bond CH stretch and the other being a carbon double bond carbon stretch. We have 1 ester peak and 1 carboxylic acid C bond O stretch. So we have this CO bond stretch at around 1200, the ester being around 1700, the alkene being around 1600, and the double bond CH being around 3000 region. So we're seeing that the peak intensity for all of these are actually pretty strong. And the shapes are ranges from sharp to broad. So when we're looking at the HNMR here on the far right here, we're able to see where we have 1 signal, right? Only 1 signal, and it is a signet. It's because of the symmetry here and the limited amount of hydrogens that is in the maleic anhydride. So this one is fairly upfield, is around 7 ppm, and we were able to see this one signal here. And so that's one of the ones that we use. We use HNMR and IR to categorize maleic anhydride, which is a starting material. Dimethyl maleate. So we are able to see the IR on the far right, the IR spec. So we are able to see alkane symmetrical CH stretch, this one being sp3 hybridized. We are able to see this around the 2900 regions. We are able to see an alkene, a double bond CH stretch around a 3000 region, an ester around a 1700 region, and a carboxylic acid CO stretch on a 1200 regions. And we're able to see this on the IR spec right here. On HNMR, there's two signals here, and that's because of the environments that the hydrogens have. So because of the different environments, we are able to see the two signals, but they're both singlets at the end of the day. So we have a one that's fairly upfield, around 6.2 ppm, and the other one being 3.7 ppm. So we are able to see these two peaks in the HNMR. So both IR and HNMR was used for characterization of dimethylmaleate. Now that we have talked about the characterizations of our starting material, maleic anhydride, and our procedure, dimethylmaleate, it is time to talk about the setting up of the reaction. So we're preparing a glassware of 300 milliliters of colonyl vial. So we have the magnetic spit in there. So we are using the calcium chloride drying to, it is used as a drying agent in this experiment because of the excess water. So we're transferring the reagents and setting up the distillation under the fume hood. So we're having the appropriate amount of methyl alcohol in maleic anhydride to the solution. Then lastly, placing 4 to 5 milliliters of concentrated sulfuric acid. So we're able to cap up this distillation, and we're adding, or after the addition of all the reactants, we heat it up for approximately 4 to 5 hours. Now, that is why we're using the condenser, because we are heating up this for a long period of time, and we need to be able to still have that that solution still be there and not evaporate. So let's move on. Product isolation purification. So the product has to be isolated and purified, as organic compounds made in laboratories contain impurities. So we often use crystallization, which is a process of forming crystals, crystallization by cooling a hot concentrated solution. Once that happens, crystals begin to separate out, and we are able to record mass of obtained product. So these are the steps right here, and we're able to use the pipettes to transfer the materials and do this. So the dimethylmaleate is able to be purified by a simple distillation. Moving on. All right, before I actually move on, let's actually wrap it up and talk about the type of the reaction that was used. So to wrap up dimethylmaleate, dimethylmaleate can be synthesized from maleic anhydride and methanol with sulfuric acid via a nucleophilic acyl substitution reaction, and this is used to form the monomethyl ester. Right? So this is followed by a Fischer esterification reaction to get our product, the dimethyl ester, which is the dimethylmaleate. Okay, now we can move on into the second part, the halogen catalyzed cis-trans isomerization to get the fumarate product. So moving on to the second part of this experiment, we're able to synthesize dimethyl fumarate. So looking at this reaction mechanism, we see that this reaction takes place using a radical reaction. So there's 3 steps needed. So there's the initiation step, which is the formation of radicals in the presence of light energy. Bromide breaks homolytically to give the bromide radical. So we have the second step, which is the propagation step, which is just to get the radical products, and the final step being the termination step, which is when the radicals essentially come back together, essentially decreasing the concentration of radicals in the system. So the rotation that we see right here, the rotation is in the propagation step is used so that we can get the transformation, essentially dimethyl fumarate. Dimethyl fumarate is used around the globe as in the pharmaceutical industry, right? As in, they use it as an oral therapy for psoriasis, which is a skin disorder. It is commonly known to treat multiple sclerosis as well. This compound has many similarities to dimethylmaleate. For one, same molecular weight, of course. So we'll talk a little bit more about those details later on in this presentation. So right here we have the experimental setup. So we have, of course, our dimethylmaleate. That's what we formed in part 1. Dimethyl fumarate is what we're forming. We have a CCl4 that is actually used. It's something that we use as an inert molecule, so that it won't really react too much. The bromide is what forms the initiation radical step, and it is important. It is an important reagent, as it is the one that is doing the homolytically that is being homolytically breaking or broken, and we are able to use the dimethyl or the dimethylmaleate as well as the bromide and the CCl4 to form the dimethyl fumarate. So let's move on. So the materials that we need is actually test tubes. Of course, we need several to place our reactants. 5% bromide solution in CCl4, as we were saying. opaque covering, this is to label. Light bulb, preferably 75 to 100 watt for energy. We're using a beaker and a heat source, of course. Okay. So these are the procedures right here, and we are seeing that the 3 test tubes, 2 of which will have the bromine. So we are actually labeling the one that doesn't have the bromine so that we can know which one doesn't have the catalyst. So we're wrapping one of the tubes with dark opaque covering, place the 3 tubes in the beaker, boiling water, and each receive the same amount of light, of course, because we don't want any, we want all of them to receive the same amount of light. So the irradiated sample containing the catalyst rapidly solidifies as a colorless crystal of dimethyl fumarate at the end. These are the steps of the procedures. So let's actually move on. The product characterization. So the product characterization that we used was TLC. TLC chromatography, because the polarity difference in dimethylmaleate and dimethyl fumarate. It is wise for us to use TLC because of this. We don't really want to use IR or HNMR for this because of the similar molecular formula as I was talking about earlier. So IR, we wouldn't really see a difference because of the similar or really the same functional groups that both dimethylmaleate and dimethyl fumarate shares with each other. HNMR wouldn't work as well. So TLC, because of the polarity difference in the 2 products, would work because that would categorize it perfectly, right? So we are able to see right here, actually, we're able to see this dimethylmaleate right here, right? We're able to see this polarity going this way, right? It is more polar, right? And in this one, it's not directly canceling each other, but it is reaching that 0 mark more than the dimethylmaleate, as far as when we're talking about polarity here. So we are able to see this TLC plate and where dimethyl fumarate is, right? So so we predict the dimethyl fumarate would be most up on the plate, or travel more as it is less polar, right? So the polarity is close to 0, whereas the dimethylmaleate, the polarity is closer to 0, or it's farther away from 0. So that's why we are seeing it lower on the plate. So, so there are also other differences between the 2 compounds. For one, the dimethyl maleate and the dimethyl fumarate have different densities, right? The dimethyl maleate has a lower density than DF, and this has to do with the structure, more hand in hand, and how really it matches up in water. And how the functional groups, where it's placed in the polarities and all of that. So this is what we see, and this is the differences, and we're able to see these differences in the isomerization product characterization of TLC. That's why we use TLC. So this was the reaction. So thank you so much for listening to this presentation. Again, my name is Don Cadet. My TA is Mr. Paul Slawek. Thank you. It was a good semester. Thank you.